Hi everyone, welcome back to Operations Research. Today we're going to talk about the new topic, nonlinear programming. So far in this course, most of time were spent on linear programming. Okay. In particular, we spent 2 weeks to talk about some other things. One is about linear integer programming, and then the other is about network flow models. Okay, two special topics. We know that network flow models are somewhat special cases of linear program. Okay, so that means this arrow here is telling us that network flow problems are linear programs. On the other hand, integer programs and linear programs, they are just different things. Okay, here variables are discrete and here variables are continuous. So we say linear programming and the integer program, they complement each other, so they do not include either one. What's new is that starting from today, we will talk about nonlinear programming. So some functions are going to be nonlinear. For all the three subjects here, functions are all linear. And starting from today, we will talk about nonlinear functions. So nonlinear programs are, of course, generalization of linear programs. Today, we will also see that linear programming is a special case of nonlinear programming, and details will be given to you later. Today, we will focus on solving single-variate nonlinear programs. Okay, actually, I will first give you some overview and the basic properties for all the nonlinear programming subject. And then we will tell you how to solve single-variate NLP. That means nonlinear programs with only one variable. Next week, we will talk about multivariate nonlinear programs. So let's start with some motivating examples. So let's consider this story. Suppose I'm a retailer. I want to buy a product at a unit cost C and then sell it at a retail price P. I cannot control the cost, but I can decide the retail price. Once I choose the retail price, the demand for the retail price is given as this linear function. Linear function is just a simplification for us to discuss the problem more easily. In general, it's just some decreasing function. Okay, so what's the form of that? Is that suppose this is P and this is dP. Then the demand function would be something like this. Okay, A minus BP, and A is here, and the slope of this function would be negative B. Now that's the basic situation. So given a price, I'm going to get a demand. Okay, and the area here, of course, is the sales revenue, the total sales revenue I can earn. So for this problem, I also have a cost. So I'm working on profit maximizing price. I want to find a price that maximizes my total profit. So regarding formulating this problem, first we recognize that there are some parameters, A, B, and C. They are given and fixed, so they are parameters. The decision variable is the retail price P, and I'm looking for P subject to this constraint. P cannot be negative. Then profit maximization can be formulated like this. I'm looking for a P such that P is non-negative, and this is my profit. P minus C is the sales margin, and A minus BP is the sales quantity. Okay, so the product of them is the sales, is the total profit. I'm solving this problem for finding the profit maximizing retail price. For some programs, if there are only a few constraints, then sometimes we will write those native constraints below the maximum sign. Okay, so this program may also be written like this to save some spaces. What's important here is that naturally the trade-off on finding a price is to choose between high quantity or high sales volume. And because there is a product operation here, we can see that P is multiplied by P. So this function is a nonlinear function of P. So that's why this is a nonlinear program. Okay? And certainly it has no way to become linear, because always the profit is the sales margin times or multiplied by sales quantity. This is always nonlinear. Let's consider another example. Suppose I give you a piece of square paper here, and the length is small a here. I'm looking for a small d as the length of h at the corner. Okay, so that means this length is d and this length is d. I'm asking, how may I cut the 4 squares and then fold this paper to create a container like this, so that I can maximize the total volume of the container? Again, I face a trade-off. Either I want a large bottom surface or I want a large height. That's a trade-off. For formulation, the volume is just the area of the bottom surface and the height, the product of them. Okay, this is my volume. I'm looking for a d within 0 and a over 2 to maximize my volume. So this is again another nonlinear program. The last example here is about locating a hospital. Suppose there are n cities, each lies at the location xi, yi. So xi and yi, they are parameters. And we want to locate a hospital at the location xy. Now xy is a place for us to determine. So xy are decision variables. What we want is to minimize the average Euclidean distance from the cities to the hospital. Formulation would be like this. Okay, I'm looking for xy to minimize the sum of all the Euclidean distances. I'm looking for the average Euclidean distance, but it's equivalent to minimizing the sum, right? So this is the nonlinear program that can solve the location problem for this particular situation. Again, it's nonlinear because we always have this square and square root. Just to remind you, the problem can be formulated as an LP if we are working for Manhattan distances. We had that example. Manhattan distances means that if this is the source, this is the destination, then we can only move either horizontally or vertically. But for Euclidean distance, we move in straight lines. Okay? So given any 2 points, in order to get the Euclidean distance, we naturally need to do these square and the square roots. And that's why the formulation must be nonlinear. We have seen many and several examples that the problem is just nonlinear. So naturally, we need to learn how to formulate and solve nonlinear problems. Okay? In general, a nonlinear program can be formulated like this. There are n decision variables. Generally, we say they are real numbers. Okay, so that means they are continuous. And then there are m constraints. Each of them is expressed as gi of x less than or equal to bi. So it doesn't matter whether inside gi there is a constant term or not. If there is a constant term, it can be put to the right hand side and combined to another constant term. So it doesn't matter. So some people also prefer to write 0 here, but again, it doesn't matter. This problem would be a linear program if all the f and g are all linear. Or, in general, we say it's a nonlinear function. In that nonlinear program, in that case, we allow these functions to be nonlinear. The study of formulating and optimizing nonlinear programs is nonlinear programming. And in general, we will see formulating nonlinear programs is easy, but optimizing it is hard. Okay? as long as we allow you to write any nonlinear functions, then we allow you to write any functions. Okay, so given a problem, formulate it as a nonlinear program is not very hard typically, but optimization is hard. Let's discuss why. So compared with linear programs, nonlinear programs is much harder to solve for two reasons. Let's see the first one. In a nonlinear program, a local minimum is not always a global minimum. Okay? Global minimum means the true optimal solution for minimization problem. And a local minimum means around that point, no point is better than it. But maybe somewhere far from this point, there is a better solution. So an example is here. Suppose this is the feasible region, and this is the curve of our objective function. In this case, we say x1 is a local minimum because at the neighborhood of x1, for those points close enough to x1, no one is better than x1, no one is smaller than x1. The similar thing happens to x4. Now, x4 is at the boundary of the feasible region, and all the feasible points near x4 are not as good as x4. Okay, so both x1 and x4 are local mean, but the only global mean is x star. Okay, this one is really the minimum point for whole the feasible region. So a local mean may not be a global mean. And then that tells us a greedy search may be trapped at a local mean. So greedy search means I start at some point and then I look for an improving direction to go. And in that case, I will end up with a local mean when I see there is no more improving direction. But that may end up with a local mean. For example, if we start at here, then we look at either go left or go right. We will see that going left is the improving direction. So we will go left until we get to x1. And then we will stop if we are working on local search. So that's not enough for solving a nonlinear program. Another observation we have is in a nonlinear program which has an optimal solution, it's possible that no extreme point is an optimal solution. So for example here, suppose I'm looking for x1 and x2 at the first quadrant to minimize x1 square plus x2 square. So I'm looking for the point that is the closest to the origin, subject to the sum of them must be at least 4. So the feasible region is of course here, and we're looking for a point that is closest to the origin. So the optimal solution is 2, 2. But in this case, there are two extreme points, 4, 0 and 0, 4. None of them are optimal. And the only optimal solution is not an extreme point. So again, this is something different from linear programming. So given the previous two observations or two facts or two properties of nonlinear programs, no one in the world has invented an efficient algorithm for solving general nonlinear programs. When I randomly give you a nonlinear program, it's possible that no general algorithm can really solve it in a short enough time. For a nonlinear program, if we really want to say something, we need some conditions. We need some results from analysis. We need to know when does a local mean implies a global mean. When do we have extreme point optimal solutions? For example, because the previous two facts prevents us from finding a general algorithm for solving NLP, so we want to ask, when may we have these conditions? If so, we can try to find some ways to solve NLPs, and that will be the main subject today. So our main tool is convex analysis. This is what people do today in the world, in the field of nonlinear programming. regarding finding conditions to satisfy these two requirements. Okay, we're going to define, we need to have some mathematical tools first. So we will first define some concepts called convex sets and the convex and concave functions, and then tell you what's convex programs, and then show that they have the first property. Okay, mainly we will rely on the first property to solve problems in this course, and that's also the general idea in the current field of nonlinear programming. Okay, so let's take a break, and in the next video we will start to talk about convex things. Thank you.